Code optimization is the machine-independent phase where a compiler transforms a program to make it run faster or use less memory. This process operates under a strict zero-tolerance policy known as semantic invariance. The optimized output must remain identical to the original for any given input. This checklist outlines the 4 strict criteria that govern compiler behavior. The first is preserve meaning. Even edge case behavior, like division by 0, must be handled exactly like the original code. The second rule is measurable speedup. The transformation must yield a mathematically significant reduction in average execution time. Third is space efficiency. Ideally, optimization shrinks the memory footprint of the compiled code. The final criterion is worth the effort. The compiler's computational time spent optimizing must balance against actual runtime saved for the user. This presents a rigid conflict. How can an automated system rewrite a programmer's logic without breaking the application? Compilers cannot read code the way human engineers do. To guarantee semantic invariance, they must geometrically deconstruct raw text into strict mathematical graphs. Before optimizing, the compiler looks at the intermediate representation of the program. Specifically, it starts with the raw, unoptimized 3-address code, or TAC. The compiler must slice this linear text into manageable units called basic blocks. A basic block operates under absolute architectural rules. The control flow can only enter at the very top of the sequence and must leave at the very bottom. There can be 0 conditional or unconditional jumps in or out of the middle of a basic block. In this diagram of raw TAC, the compiler uses a scanning algorithm to identify specific lines, known as leaders. The first rule of identifying leaders is simple. The compiler always flags the absolute first statement of the code as a leader. The second rule targets jumps. Any statement that is the destination target of a jump command is immediately flagged as a leader. The third rule catches the fallout. Any statement immediately following a jump command is also flagged as a leader. With the leaders identified, the compiler draws structural boundaries. It groups the code starting from one leader down to the line just before the next leader, formally creating discrete geometric blocks labeled B1, B2, and B3. These individual blocks form the foundation of a macro structure known as a flow graph. Directed edges connect these nodes together. An arrow snaps from block 1 to block 2, representing the actual paths of execution the program can take. Translating flat code into a rigid flow graph establishes isolated mathematical scopes. This exact structural foundation provides the rigorous framework necessary for the compiler to confidently automate complex, algorithmic code transformations safely. With the graph built, the compiler applies local optimization. These are transformations strictly confined within the boundaries of a single basic block, completely ignoring the rest of the program. To prove these transformations preserve meaning, engineers evaluate a strict before and after state for every change. The first local transformation is common subexpression elimination, or CSE. Looking at this split-screen comparison, we see a basic block computing 4 times I twice. In CSE, the compiler identifies this identical, previously computed mathematical expression. To avoid recalculating it, the system routes the stored value directly into the new variable. The second transformation is copy propagation. This technique takes a direct assignment, like x equals y, and substitutes that original variable y into all subsequent equations downstream. As you can see, z equals 3 plus x transforms into z equals 3 plus y. Next is dead code elimination, a process which actively targets operations that compute values the program never actually uses. This naturally pairs with copy propagation to purge leftover obsolete assignments. It also deletes unreachable logic. If a debug variable is hard-coded to false, the compiler recognizes the if block is dead code and deletes it. The fourth local transformation is constant folding. If an expression contains only constant arithmetic operands like 2 times 3.14, the compiler evaluates the math at compile time, collapsing it to 6.28 to bypass unnecessary runtime processing. While these local transformations effectively strip away redundant micro-operations, they only optimize a linear path. The most significant execution cycles remain hidden in the program's global structure. This visualization of the flow graph shows exactly where we find those massive cycles. We shift our focus to nodes where the directed edges form a continuous, repeating cycle, a loop. The reality of software execution is that the vast majority of processing time is spent trapped inside inner loops. Because execution time is so heavily concentrated here, loop optimizations provide an exponential return on investment and dictate the compiler's primary focus. There are three core techniques used to accelerate cyclical flow. The first is loop-invariant code motion. The compiler scans the loop for any calculation that produces the exact same result every iteration. Here, the expression limit -2 is extracted entirely outside the loop bracket, computing once as a static assignment instead of repeating endlessly. The second technique is strength reduction. This targets a hardware reality. Certain CPU operations, specifically multiplication, cost significantly more clock cycles than simple addition. Watch the code block. An expensive multiplier circuit tied to a loop index is completely replaced. In its place, the compiler substitutes a faster accumulating addition operation. The third technique is induction variable elimination. Within a single loop cycle, multiple variables often increment identically in sync. These are called lockstep variables. The compiler systematically deletes one of these redundant lockstep variables. It strips out the variable I, leaving T to control the loop single-handedly. This frees up critical hardware register space without breaking the loop's logic. Prioritizing these structural loop transformations yields massive performance gains. The highest impact optimizations are those that restructure the program's cyclical architecture. Beyond single blocks and loops, the compiler executes global optimization. This is the process of applying function-preserving transformations across multiple discrete blocks simultaneously. But this introduces a severe risk. As control flow moves across the graph, variables constantly change state. Optimizing blindly at this scale risks critical data corruption. To mitigate this, compilers use a sophisticated tracking system called data flow analysis to map exact data movement. This diagram illustrates the first tracking concept, reaching definitions. Watch as an assignment in block 1 traces down the directed edges, proving it physically reaches block 4 without being overwritten. Reaching definitions allows the compiler to mathematically prove whether a variable assigned in block 1 will successfully survive the journey to impact block 4. The second tracking concept is live variable analysis. This evaluates whether a value currently sitting in a hardware register will strictly be needed for a future execution path. Here, a forward scan confirms the variable is never called again, marking the node as dead. Once the analysis determines the variable is dead downstream, the compiler forcefully reclaims that register space for new computations. The compiler's ultimate objective is the production of a semantically identical, structurally superior graph. Its success depends on balancing the mathematical weight of global tracking against the exponential speedup of the final executable.